Okay, the cyclone has passed from here, but it's still waiting to slam into Gujarat, which is not going to be very nice. But COVID is still here, and climate change is still here. But S2S is a time scale which hopefully will allow us to use it as an adaptation tool to climate variability impacts that happen on these day-to-day timescales. And the next section here is land surface processes relevant to S2S seasonal S2S predictions, so sub-seasonal to seasonal predictions. You may know some of these names. Paul Meyer, for example, is quite famous. You always find such complicated figures for ocean, land, atmosphere, Earth system, and so on. They are very useful, but mostly as a schematic. Obviously, they are captured in models to some extent or the other, and then there are issues about how is the model formulated and how can it be validated. Are there really data available to validate these kind of connections, interactions, feedbacks, and so on? And then there's a question of where the skill comes from, especially at S2S timescales. So going through this, we have colored arrows here pointing to radiation, surface layer and atmospheric boundary layer, land surface processes in this soil color of brownish. So there are positive feedbacks for C3 and C4 plants. I think if you don't know what that is, don't worry about it. It's the pathways of photosynthesis where they have different properties in terms of their dependence on temperature and CO2 concentrations and so on. Negative feedback for CAM plants, another class of plants, and negative feedback for optimal temperatures. So we have very complicated looking systems with being forced by incoming solar, but the atmosphere also sends downward long wave radiation. Vegetation cares for something called photosynthetically active radiation, which tends to be, let's say, about 50% of the incoming solar. And there are albedo factors for land, which depends on vegetation types, which depends on soil moisture, which depends on desert land use types and urban canopies and so on. So you have all these processes. If you start here with radiation 1, so emitted long wave and surface temperatures being affected by both long wave and short wave, so that's going to affect land processes, evaporation, transpiration, vegetation, albedo dependence, and so on. Number 2 is down here, vegetation. So there is the evaporation and moisture flux, and then there is transpiration, which is from the vegetation. So evapotranspiration is the keyword, which is basically evaporation mediated by vegetation. 3 is here, relative humidity. So land atmosphere exchanges are going to depend on sensible and latent heat, with of course long wave as well. And sensible can be strong for land because the land can warm up pretty fast. So if you think of heat capacity, atmosphere has the lowest, then comes land, and then comes ocean. Ocean has the highest heat capacity. But heat capacity is also memory, which gives us predictability. So soil moisture plays a critical role in that, in terms of also feeding back to the boundary layer processes, as we will see, and then clouds and so on, which are shown here. So I won't go through all this, but you can see reflectance by albedo processes, canopies. So there are negative feedbacks above optimal temperatures, positive feedbacks. Do we see any other feedbacks here? Okay, so all these feedback to soil moisture, soil heat flux, and soil temperature. And there is the reflected albedo term shown here. So urban heat islands, all these other things fit into land processes. So the boundary layer processes are here in terms of turbulence dependent on humidity and temperature and cloud processes, etc. I should have put this later, but this is from the National Academy book that is shown here, and it's talking about the Earth system prediction at various timescales and the infrastructure needed. So engage end users, improve predictions of disruptive events, and here is our timescale S2S, which needs cyber infrastructure and trained workforce as well. So we need to include more Earth system processes, which doesn't completely include here, for example, the biogeochemistry, the N2O emissions, methane emissions, CO2 emissions, and so on are also important in the end, depending on the time scale. Okay. Land is critically different than the ocean in terms of a very strong diurnal cycle because of its low heat capacity. Ocean also has a diurnal cycle and is very dependent on the location. People who do sea surface temperatures, for example, worry a lot about diurnal warming layer in the ocean as well. But land has a very strong diurnal cycle, so you can see the process here starting in, let's say, midnight. There is typically a land in the temperature inversion, so the boundary layer is made stable, and there is a residual layer that is left over from daytime warming and mixing where convection, dry or moist convection happens. So then by the time sun sets, you again begin to establish the stable boundary layer and temperature inversions. So the warming of the boundary layer and its growth during the daytime begins to create moist processes that affect free tropospheric processes like cloud heights, cloud base. So there are interesting soil moisture feedbacks that affect these land impacts on cloud processes. This is another way to look at it. If you look at wet soils and dry soils, you can clearly see the change in the boundary layer height here. So you have latent and sensible heat fluxes. So when you have vegetation and wet soils, latent heat flux, evaporation, evapotranspiration tend to be important processes compared to sensible heat flux. And of course you have the net radiation and the whole weather forcing. So the boundary layer here is constrained in terms of its exchange with the free troposphere, whereas in a dry land you have much more sensible heat flux than latent heat flux, but sensitivity to soil moisture can be high here, which affects predictability and prediction skills and so on, but soil moisture is very low in the dry soil. So those kind of interesting feedbacks happen, but this anyway increases the boundary layer height over dry soils. Okay, so let's leave this here and then come to some details on how land processes have been understood over time, even starting from the time of Leonardo da Vinci, who was thinking about it under some context, and how land models have evolved and what processes are relevant for the S2S predictions. Okay, so this is a nice little chapter. All these, as you can see from the podcast, they are short. I have added lots of figures from my own searches and added many points, but each chapter, as I said before, has lots of references that you can go through to find the details which are not included explicitly in these short podcasts.